This video is the fourth video in our ongoing tutorial series on CCNA. In it, we will learn about CSMA/CD, half-duplex, full-duplex, collision domain, and broadcast domain. Let us start with the basic concepts we need to understand these terms. When a device sends data to another device in the network, it goes through several steps. A networking model describes these steps. The TCP/IP is a networking model. It includes standards, protocols, specifications, addresses, and all other things devices require to communicate in the network. It divides the communication process into 5 layers: application, transport, internet or network, data link, and physical. We will discuss these layers in detail in upcoming videos. In this video, we will learn only the relevant portion of each layer. The application layer of this model defines standards, protocols, and specifications for applications that exchange data with other devices in the network. It prepares the data stream for transmission on the source device. A data stream can be any meaningful data file. For example, it can be a text file, software, video, or an image. It can be significant in size. For example, an iOS image file can be 5 to 10 gigabytes. However, the media that connects the source and destination devices can differ in size. If it is less, the source cannot send the whole data stream at once. It must break the data stream into smaller pieces. The transport layer does this job. It breaks the data stream into smaller pieces. Each piece is called a segment, and this process is called segmentation. It adds a header to each segment. A header includes information the destination device requires to reassemble the data stream. After adding the header, it gives them to the network layer. The network layer also attaches a header to each segment. The header includes the source and destination IP addresses. With the network layer header, the segment is called the packet. The network layer gives packets to the data link layer. The data link layer adds a header and trailer to each packet. The header includes the source and destination MAC addresses. At the data link layer, the packet is called a frame. The data link layer gives frames to the physical layer. The physical layer converts frames into signals and loads them to the connected media. Signals travel through the media and reach the destination device. If there is an intermediate device between the source and destination, it processes the signals. The processing depends on the type of the device. There are 4 types of network devices: Layer 1 devices, Layer 2 devices, Layer 3 devices, and Layer 4 devices. Layer 1 devices understand only signals. A hub is a Layer 1 device. It amplifies incoming signals and forwards them from all other ports. A switch is a Layer 2 device. It converts signals into frames, reads source and destination MAC addresses from each frame's header and makes forwarding decisions based on them. A router is a Layer 3 device. It converts signals into frames and frames into packets to make forwarding decisions. It uses source and destination IP addresses to make forwarding decisions. A multi-layer switch is a Layer 4 device. It converts signals into frames, frames into packets, and packets into segments to make forwarding decisions. It provides many additional features. However, it is one of the most expensive network devices. A network can have 1, 2, or all 4 types of network devices based on its requirements. Now that we have a basic understanding of how network devices process signals, let us understand how the cables transport signals. A cable creates an electrical circuit between the source and destination devices. The source device puts signals on this circuit. The destination device reads signals from this circuit. If the destination device wants to reply, it must wait until the circuit becomes free. Once the source stops sending signals, the destination device can respond. The same rule applies to the source. If it wants to reply, it must wait until the destination device's transmission ends. This type of communication is called half-duplex. In half-duplex, a device can only send or receive data at a given time. It cannot perform both actions. However, if the cable provides 2 circuits, and devices can perform both actions simultaneously. They can use one circuit to transmit and another to receive the data. This type of communication is called full-duplex. In full-duplex, a device can send and receive data simultaneously. In earlier days of computer networking, coaxial cables were used to connect end devices. A coaxial cable creates only one electric circuit. Since it establishes only one electric circuit, it works in half-duplex mode. Later, the coaxial cables were replaced with Ethernet cables. An Ethernet cable creates 2 circuits, one for sending and another for receiving the data. Since it makes 2 circuits, it works in full-duplex mode. Apart from cables, intermediate network devices also affect the transmission. If an intermediate network device does not know how to keep one device's data separate from another, and devices will work in half-duplex mode regardless of the cable type. An intermediate network device can filter data only when it works in layer 2 or higher. If it works only in layer 1, it cannot filter the data. For example, hubs and repeaters are layer 1 devices. They understand only signals. Signals have no identification marks. The intermediate network device cannot make accurate forwarding decisions based on the signals. To deal with this situation, it implements the CSMA/CD mechanism. The CSMA/CD mechanism allows layer 1 network devices to forward signals of multiple devices in a queue under certain conditions. Let us understand this mechanism in detail. Since layer 1 devices in half-duplex mode create only one electric circuit for transmission, this mechanism allows only one device to send signals. If another device wants to send the signals, it must wait until the circuit becomes free. For example, we have 3 PCs on this network. Let us suppose PC1 sends signals to PC3. In this case, PC2 cannot send signals to any other PC. PC3 can only receive signals. If it wants to reply, it must wait till the transmission from PC1 ends. Devices check the connected cables to know whether the media is free for transmission. If they see signals in it, they do not start the transmission. In CSMA/CD, this process is called carrier sense. For example, if PC2 wants to send the signals, it must check the cable before it starts. It can send signals only when the cable is free. Since cable is not free right now, it cannot send the signals. It can send signals only when it will become free. This mechanism ensures that only one device sends signals at a time. As long as it is true, all devices can send signals. However, networks do not always work as expected. Sometimes, they may work unexpectedly. This mechanism defines this situation as multiple access. It occurs when the media is free, and 2 or more devices want to send signals simultaneously. Let us suppose PC1 and PC3 want to send signals to PC2 simultaneously. They both sense the media at the same time. Since the media is free for transmission, they both put their signals on their connected cables. When it happens, signals collide at the hub. This mechanism defines this situation as collision detection. If a device sees a collision for its transmitted signals, it retransmits them with a jam signal. This jam signal informs all recipients about the collision. After sending the jam signal, it waits for a small random period measured in microseconds and senses the wire again. If collision still exists, it repeats the same steps. If it sees no collision, it retransmits the original signals. Since devices wait for a random period, the device whose waiting period is over starts the retransmission first, and the remaining device waits till it ends. This way, CSMA/CD allows layer 1 devices running on half-duplex to send and receive data. Now that we have learned how CSMA/CD works, let us understand the collision domain. A collision domain is a group of devices affected by a collision. For example, when a collision occurs in this network, all 3 devices are affected by it. Since they are all affected by it, they belong to the same collision domain. However, this situation changes if we replace this hub with an Ethernet switch. An Ethernet switch creates a separate circuit between the source and destination. When it receives incoming signals, it converts them into frames and forwards them only from the port connected to the destination. It uses the source and destination address of the frame to make forwarding decisions. If PC2 wants to reply, it can start responding immediately. It does not need to wait until PC1's transmission is over. We will learn more about this in upcoming videos. By now, remember an Ethernet switch creates a logical circuit between the source and destination devices. It forwards frames only from the port connected to the destination device. It works in the full-duplex mode. These features create a separate collision domain for each port of the switch. For example, an 8-port switch creates 8 collision domains. However, connecting a port to another switch or a higher-level device such as a router or multi-layer switch does not create a separate collision domain. Connecting 2 switches creates only a signal collision domain between them. Let us take a few examples. Here, we have a hub connecting 4 PCs. We have a single collision domain since a hub works only in half-duplex and a single collision domain. Now, let us add a switch to this network. Can you guess how many collision domains it has now? Right now, it is only one collision domain. We used one port of this switch. It creates one collision domain. We have a LAN segment running on a single collision domain. As we know, connecting 2 collision domains does not increase the total number of collision domains. Here, we extended the existing collision domain. We did not create another collision domain. Let us add 2 PCs to this switch. Now, how many collision domains it has? Adding N devices to switch ports increases collision domains. Now, this network has 3 collision domains. Now, add a router to this network. A router port creates a single collision domain. A switch port also creates a single collision domain. Since connecting collision domains does not increase the total number of collision domains, we will count only one here. Now, this network has 4 collision domains. 1, 2, 3, and 4. Now, let us add a few more devices. Can you answer how many collision domains it has now? Now, it has 7 collision domains. It is a connecting link of 2 collision domains. So, we will count it as 1. An N device is connected to this switch port. So, we will count it as a separate collision domain. It is a LAN segment. Connecting a LAN segment to a switch port creates 1 collision domain. There is one more thing to remember. A WAN connection does not create a collision domain. A WAN connection connects 2 routers. If we connect another router to this network using a WAN connection, the collision domains will not increase. However, the collision domains will increase if another router has LAN segments. For example, if we attach a switch connected to 2 PCs to this router, the collision domains will increase to 10. Now that we know how the collision domain works, let us understand the broadcast domain. A broadcast domain is similar to a collision domain but works on layer 3. It is a group of devices that share the broadcast messages. A broadcast is a layer 3 message. It reaches all devices within the broadcast domain. Since it is a layer 3 message, only a layer 3 device can understand it. Routers are layer 3 devices. They define a boundary for broadcast messages. Like a switch port, each router interface creates a separate broadcast domain. For example, this network has 2 broadcast domains. By default, only routers create broadcast domains. However, we can use switches to create broadcast domains. Switches have a unique VLAN feature that allows us to create broadcast domains. VLANs create a boundary for broadcast messages. A broadcast message generated in a VLAN reaches all devices inside the VLAN. It does not go outside the VLAN. If 2 devices belong to different VLANs, they do not exchange broadcast messages. We will discuss this feature in more detail in upcoming videos. That's all for this video. If you have any suggestions, comments, or feedback about this video, please share them in the comment section given below.